Hello everyone. Here we are presenting our presentation in this slide. The topic of our presentation is wave function. In this slide, we want to know about the wave function. What is wave function? A wave function in quantum mechanics describes the quantum state of an isolated system of one or more particles. There is one wave function containing all the information about the entire system, not a separate wave function for each particle in the system. Its interpretation is that of a probability amplitude. Quantities associated with measurements, such as the average momentum of a particle, can be derived from the wave function. Now we can see the comparison of two different wave functions that are solution of the Schrodinger equation but not standing waves. We also see the comparison of classical and quantum harmonic oscillator conceptions for a single spinless particle. In this slides, we can see properties of valid wave function. Now we can describe boundary condition. In order to avoid infinite probabilities, the wave function must be finite everywhere. In order to avoid multiple values, the wave function must be single value. For finite potentials, the wave function and its derivative must be continuous. This is required because the second order derivative term in the wave function must be single valued. They must approach zero as x approaches infinitely in order to normalization. Now we can see the interpretation of the wave function. Normalization condition allows unknown constants in the wave function to be determined. Here we can see our particle in a box where there is a wave function. Since in this case the particle is confined by infinite potential varies, we know particle must be located between x equals 0 and x equal to L. So the limit should be 0 to L. Here we can see the interpretation of the wave function. We can see the figure of psi of x and psi of x square. If n equal to 1, the only one wave where this wave is bigger, in that case of psi of x square. But when n equal to 2, there is two waves, and in psi of x square, two waves should be in positive position. And if n equal to 3, there are three waves, and these three waves should be in positive position in psi of x square. Schrodinger, a wave function for electrons. Here energy equal we know s cut omega and momentum p equal to s cut k. Schrodinger guessed that there was some wave-like quantity that could be related to energy and momentum. Here we can see various wave functions and del psi of del t equal j omega psi. We can write it in the energy terms and also momentum. Time dependent Schrodinger equation. Here I equal physics notation, and here total energy term is equal the kinetic energy term and the potential energy term. The kinetic energy term and potential energy term, the sum of is called the total energy term. S cut by divided by 2m, and del x square psi of xt is called a kinetic energy term, and b of x and psi of xt is called a potential energy term. Time independent Schrodinger wave function is also given below. Now we can see the electronic wave function. Here is the free particles wave function. Completely describes all the properties of a given particle. And psi equal to psi of xt is called a complex function of position x and time. The quantity psi square is interpreted as the probability that the particle can be found at a particular point x and a particular time t. Here we can see the Werner Heisenberg, who born in 1901 and died in 1976, and who describes the actual electronic wave function. Schrodinger equation in a wave function for electrons. For free particles, we know energy equal momentum is square divided by twice m. And we can see the free particle Schrodinger wave function. Here we can see another here we can another Schrodinger image of in the public domain. 1887 to 1961. Now we can see the comparing electromagnetic waves and wave functions. Electromagnetic waves omega square equal to c square q square, and quantum mechanics wave functions E equal momentum square by twice m plus voltage. Here you can see the various equations for waveguide and quantum wheel. Now in this slide we can see the hydrogen wave function, and here is describe this equation, and the Schrodinger equation is linear. This means that the solution to each wave function can be added and multiplied by scalars to form a new solution. The superposition principle of quantum mechanics: if psi and phi are two states in the abstract space of states of a quantum mechanical system, then a psi and b phi is a valid state as well. Here we can see the traveling waves of a free particle. We can see the spark in this figure, and here in x-axis psi of x square and psi of x in real term, we can see this wave function of the particle. This presentation is submitted by MD Sabbir Hasan, and ID is 1202051147, and also submitted by MD Asif Zaman, and ID is 1202051136. Thank you for watching all the slides.